Hello, the whole 10 people who showed up this cold morning. Now is to give you the framework to think about how you're going to approach managing multiple activities that your operating system is going to support on top of SEL4. Okay, so we're building a system. We're hoping our system will be useful and general purpose and support a wide range of activities on top of the operating system. That implies that the system that you're constructing has to deal with lots of concurrent activities at the same time. Okay? So those activities can be potentially overlapping. Overlapping in the sense that you may have multiple outstanding requests to I/O that aren't serviced in a FIFO manner. So if you get 2 requests, you may, from the application via a system call, you may issue both of those requests to the device and see which one comes back first, as opposed to only ever issuing one outstanding request at a time. Okay? Only issuing one outstanding request at a time will effectively serialize every request to the worst case latency of whatever device is that you're interacting with. Okay? So that would be pretty unsatisfactory. Lots of activities are potentially interdependent with each other, as in some activities can only proceed when the results of some other event are available to be used. Okay? So an example of this might be a page fault to a location in virtual memory for some code. That isn't going to be resolved until that code is actually fetched from the file or from swap space in order to allow it to proceed. Okay? I think I've largely covered most of that. The last point at the bottom there is that the operating system itself, which you're effectively writing on top of SEL4, defines or you have the opportunity to define what the execution model might be. Okay? You're using a low-level language like C, which provides very little support for any kind of model of execution. Okay? And you've got a fairly minimal runtime that doesn't provide you any help for an execution model. So you've got pretty well much complete freedom of how you might want to build or structure the execution model on top of SEL4. Okay? So just to contrast that with, for instance, writing applications on top of, say, Linux, you've got the POSIX threading library to pick as an execution model. You've got a whole lot of support there in order to be able to run concurrent activities and applications at the same time. There's already a predefined model inside Linux that's this process-oriented model where there's a thread of control for each thread of execution that exists in applications, and you can leverage that to basically deal with multiple things within something that you might be writing inside Linux. Okay? We don't dictate what it is that you might want to build on top of SEL4. Okay? This is kind of weird. Bingo. Thank you.
Have you posted the lecture slides and would they be the same
No,
as last year's?
they're not. Minimal change, but they're not the same as last year. I've been tweaking the last couple of days. I do generally have slide numbers if you want to take notes and you can cross-reference. Okay, so we're going to have a look at these execution models in some more detail. Okay, events, coroutines, threads, and continuations. Okay, and these are all models of managing activities in a software environment. Okay, what I will mention as a caveat is the focus of this is on a uniprocessor for now. Okay, I'm not looking at multiprocessors until later in the course, where we'll look at multiprocessor management. Completely distracted now. So for now, we're assuming a single thread of control, which you can think of as a single thread running on top of SEL4. What are you going to do with that thread? Okay. While SEL4 does provide you with the ability to create more threads, you can almost think of them as virtual CPUs. So you can spin up as many CPUs as you like, or you can come up with a model where you're only using a single thread of control on SEL4 to manage all the activities. Okay. So, the event-based model. So I'll talk about the mechanics to give you a more foundational idea in a moment, but at a higher level, the event model has this idea of some kind of external entity or even internal entity that generate events, okay? The bit of jargon that generally gets used is something posts an event, and once the event is posted, we would like to react to that event, okay? And these might be keyboard presses for I/O, mouse clicks, system calls, or interrupts. Okay? Now we have an event loop that waits for events and calls the appropriate event handler. This is kind of about the level that I described it in the early OS course. And the important restriction here on event handlers is that the event handler is a function that always runs until completion and returns back to the event loop. Okay? So, here's a model of a CPU and memory that I'm going to reuse a few times. So I'll spend a little bit of time introducing it now. So we have a really simple CPU here on the left. And it has fairly minimal state. It has a program counter, a stack pointer, and some registers, and computation on our behalf. Okay. We have a memory over here in the middle, and it has code stored in that memory. It has some data, and it has a stack. Okay. We have the program counter currently pointing at the event loop, and we have a stack pointer pointing to somewhere on the stack. Okay. So with this model, we have the event loop waiting for an event to be posted. When an event is posted, it basically matches the event to the event handler, calls the event handler, and the event handler basically processes the event and returns back to the event loop. Now that applies a few things here. Okay? There's no opportunity to block inside an event handler. If something's not ready or you can't progress, you're kind of stuck. Okay? It implies that you have to return back to the event loop and come up with a way of structuring your system such that either everything is ready when you get the event loop, or you can somehow split the handlers into multiple small pieces so that effectively a different kind of event is generated when the handler can continue in a new invocation of a slightly different handler. Okay? So there's no way the event model is basically going, issue a disk request and I'll wait for it to show up. No, you've got to return back to the event loop, and then you'll get an interrupt from the disk which generates a new event, and then somehow you'll match up the interrupt with the original invocation to satisfy the system call to read the disk. Okay. There's also no yielding, and I guess I should probably introduce that term. So the idea behind yield is that we're executing along and we've got nothing to do now because we're waiting on something. Call yield, and yield basically schedules something else from where I'm executing now. Okay, we can't do that in the event model. Okay, there's no way of allowing something else to run without returning back to the event loop. Okay, so you can see this model is getting quite restrictive. Now, also no preemption of handlers. Okay? So we're not switching between multiple handlers running at the same time. We've just got a single handler and effectively a single thread of control that goes from the event loop into a handler, and then the handler goes back to the event loop, and then we may go to a different handler, which then goes back to the event loop, and so forth. Okay? Now, the advantage of this model, and I'm going to talk more on Thursday about the pros and cons of events versus threads. I've got 2 nice talks to have a chat about that goes into that in some detail, is that we only need a single stack to support execution inside our little environment, be it inside the operating system or be it inside an application. Okay? Because effectively the local variables allocated inside handlers basically just build on the stack with each invocation. So that's the event model. So here's another little diagram, pseudocode. And I'm going to again reuse this over and over again in a few different contexts. So I'll spend a little bit of time entering it. So what I've got here is a global variable A and a really weird function that basically returns one of 2 values. Okay? So A is a global. Run at 1 in this function when the function gets called. If A is assigned 1, assign 2 to A, and then we return whatever it is that we have when we get to the end. And I'm really glad some students have shown up today because this is kind of the interactive bit, which will be kind of weird with nobody else in the room. What's the value of A that's returned in this particular example?
2.
Yes, it's not rocket science or tricky at all. It's super straightforward. Okay. So if this isn't an event handler, an event handler in an event model, the nice thing about it is there are no concurrency issues within the event handler. Okay, there's a single thread of control through the entire event model. And so we have no concurrency issues here on a global variable A. We can make the assumption in the event model that between here and here, there's no concurrent activity. Okay? There is a single thread of control from start to finish with no parallel activities. So this makes life much easier reasoning about what the code is doing. And we'll see more of that as I build on some alternative models. Okay, so if I've got an event-based model inside my kernel, and it's on a CPU with protection, okay, because that previous CPU that I introduced to you basically only had one view of memory, no user level, kernel level. So I've sort of illustrated kernel mode, user mode, by basically dividing memory up into 2 parts, where we've got the kernel data here on the left, and we've got the user mode view of the application here on the right. That how do we basically come up with a way in the event model to deal with this general purpose operating system that runs multiple processes at the same time? Okay, so here we've got one process, and with the picture here, what I'm doing is basically being the usual view of one process at a time on the right-hand side. Okay. So there's a few things missing here in the model, or questions that you might be asking yourself to try and complete this idea of, oh, I've got an event model inside the operating system, but I've got a process model inside the application. It's just like, well, how does scheduling work then? Okay, how do we sort of match the currently running process with what's going on inside the operating system? Okay, because we've got an event model inside the OS, but we've got a process model inside the application. Well, the way one can structure this is that we need to introduce the idea of what the currently running process is. Okay, it's not exactly rocket science. We need to be able to store per process state somewhere in the system that the operating system can interact with. So here we've got the yellow process A, and that is associated with the yellow code that happens to be set up at the moment. And we've got a hand here that deals with timer interrupts. Okay, it's just the event model. So what we can construct is a system where we arrange for timer events to be posted. The operating system gets control, says, okay, what do I need to deal with? What event do I have? No, it's a timer event. Let's call the timer event handler, which happens to be the scheduler. The scheduler can choose something to run. So the scheduler basically can update what the current process control block should be. This is not actually switching anything yet. And then the timer handler can return back to effectively the event loop, okay, because we end up having that exception handling funnel on the entry point of the operating system where all the system calls and interrupts and so forth go. And the code basically demultiplexes what's going on and calls the right part of the OS. That's sort of like the event model. And then once we have finished dealing with the event, then we'd return back to that assembly code that restores the application. Now, the idea here is that we'd actually have that assembly code not restore the application that is currently running, but restore the application that current TCB happens to point to on the way out. And that's where the switch would happen. So effectively, all the processing inside the OS is related to event handling in the current event. And the timer event triggered a switch of the current PCB such that when we exit back out of the operating system, instead of loading up process B, we end up, process A, we end up loading up process B, and the switch has happened. Okay? So if you remember OS 161, the switch actually was happening within inside the operating system code as you're interacting via preemptive scheduling. Okay? The idea here is that the switch only ever happens on the way out of the operating system as a result of what the current process pointer points to. Okay? And so you can build an operating system that's event-based that supports what would be a fairly traditional view of what a process is with a multi-threaded environment using this. Okay? So any queries? Should give you a chance to digest. Nope? Okay. So let's make life a little bit more complicated to make the model a little bit less restrictive. So basically what I'm going to do is build on what we have to relax the restrictions that we've put in place to keep our life simple. In return, we're going to have to deal with some more complexity. Okay, so let's introduce coroutines. Coroutines have been around for quite a while. They were first kind of meant back in 1963. Okay. And originally they were described as analogous to a subroutine, which you can think of as okay, with an extra and exit point, okay, which is probably hard to grasp what even that means at the moment. I think the easy way to grasp that is the extra exit and entry point is via yield. Okay, so the idea with yield is that if I'm executing some code and I get to a point right here where I'd like somebody else to fill some time, I can call yield and the OS will switch to some other activity where it can potentially call yield. And the OS may choose to schedule back in this direction, and then we continue down the slide. And so the extra exit and entry point are effectively these two, actually it's getting messier by the minute, these 2 points here and here. Okay, so we're executing along, and we've got an extra exit point because we call yield, and we've got an extra entry point because it returned from yield. Okay. So the idea behind this is this can now allow us to support long-running subroutines, i.e. long-running handlers. Okay. So what we can do now is that, what's a good example? So imagine in our event-based system, we've got a system call that needs to really run for about 10 minutes. I don't know what it's going to do. I'm going to compute the weather for here. Okay, and that long-running routine obviously would not be satisfactory in an operating system to have the system hang for 10 minutes while that event was processed. So what we could do by introducing coroutines and this idea of yield is that in judicious points in the giant matrix multiplier that is weather simulation, put in a yield at various points so that we can compute a bit, yield so somebody else can do something, compute a bit, yield so somebody else can do something. So the onus here is on the programmer to basically control the length of computation before some other activity gets a chance to run. Okay. It also allows us to build synchronization primitives that are actually very ideal in some sense, where we can say while a condition is not true, i.e. waiting for something, we can call yield. So rather than busy wait for something to occur, what we're doing is basically yielding to something else in the system while we're waiting, in order to utilize the system more efficiently, rather than just burning CPU cycles waiting for a flag to change. So, here we have our model again. So, yield ends up saving the state of a coroutine and starts running a different coroutine. Okay? That implies we have to somehow preserve what was going on inside A, and we need to keep track of what was going on inside B in order to be able to restart it. Okay. Again, there's no preemption here. It's like the event model, where there's sort of no interrupts and switching and so forth in between one thread and another. It's all explicitly called by you, the programmer. So, here's our example that we had before, where we've got a coroutine-like model, where we assign A, we yield for some reason, because assigning A takes a long period of time, and then we've got this test and the up. Okay. So my question is, what is the value of A? And we've got a 2.
It's either 2 or whatever some other process sets it to.
Bingo, the answer that I was looking for. So the answer here is it depends now, because we've called yield. Yield results in some other activity being able to progress. So the value of A now is dependent on whatever that activity was, and if this code, we don't know. So really, A is kind of undefined now. Let's change it slightly. What's the value of A now? 2. Yes, everyone gets it really quickly. And that's because we can assume in the coroutine model that there's no concurrent activity before the yield and no concurrent activity after the yield. So this is nice from a programming perspective for you to reason about what's going on. Okay? You can assume that the only time something can occur is inside a yield. Okay, so there's limited concurrency, and you can assume access between yields. Okay, so how do we go about implementing coroutines? Okay, so coroutines are usually implemented with a stack per routine. So we should be able to save progress within that particular function that I introduced at the point of the yield, and then we need to be able to resume progress of a different coroutine at the point where it yielded. Okay. So in this particular example, routine A is currently loaded, okay, represented by where the arrows point to here. And routine B is stored on routine B's stack. Okay? So in order to switch from A to B, that involves saving the state of A. And we're assuming in a simple world that the state of A is basically entirely captured by the CPU. Okay? And we want to restore, i.e. load the state of B into the CPU here. So we want to update the CPU so that it now points to B rather than A while preserving A. Okay. So you've seen this code in the basic OS course doing thread switching, but actually we can leverage it to implement yield as well. So I'm using the MIPS example because we're all familiar with MIPS from the previous course. So I'll continue using that processor. So the idea is that saving of the progress from where we're up to is that we're going to save it onto the stack that we now have per coroutine. So we reserve some state on the stack by decrementing the stack pointer, because we all remember stacks grow down. Then we save the registers that the compiler expects to be preserved whenever it calls a function. Okay. So as long as yield leaves in place what the compiler expects when it generated the code surrounding the yield, as long as all that stuff is still in place when yield comes back, it doesn't really matter what goes on in the system. Okay. It'll be completely transparent to the code that's running, as long as we preserve what the compiler expected to be preserved when the code called the yield function. And so that basically means it needs to save some of the registers that are defined as not changed by callees when a caller calls a function. So this should be a relatively familiar, if not a little distant in the past term. So once we've stored this on the stack, we need to store the stack pointer that basically represents where we've basically got to at this point. And we store the stack pointer into A0, and A0 basically points to the process control block, or sorry, not the process control block, the coroutine control block, where we're going to keep track of where this stack pointer was when we switched away from this coroutine. So given that this is how we save the state of the current coroutine, anything we switch to must have been in exactly the same state, because they will have called yield in the past and stored things in exactly the same format. So by changing the stack pointer, by loading the stack pointer for the coroutine we're switching to, we've now switched stacks. And now when we unwind and load those registers up off the stack, we're loading it up for the coroutine that we've switched to, because we're running on their stack now, not the stuff that we've just saved. Okay? So switching the stack pointer actually did the switch.
The previous line had 8 zeros the previous time. Was it intentionally 8 1?
Yes, that's the second argument. Sorry. So rewinding, argument passing convention on the MIPS is that a 0 is the first argument, a 1 is the second argument. And so the two arguments to this particular function call to do the switch is a pointer to the coroutine control block that you're switching from, i.e. the current one, and the coroutine control block that you're switching to. So given those two, A1 is what we're switching to. Okay, so good question. Had assumed that, funnily enough, that you all remembered exactly what we were talking about 2 months ago. Okay, so when we return to the return at the bottom here, that's going to be returning to the coroutine that we've switched to, the code that called yield in that coroutine so that it can make some progress. Now, I can see a few eyes go over. Whoops. So to make it clearer, let's have a look at just the flow of execution using yield, using two coroutines. So if we call yield at this particular point here, we save those registers, expect that the compiler expects for the code that's actually running here that calls yield to be preserved, save them on the stack of A, switch stacks, and restore the registers and return to the code that was in routine B. Then it gets to a point where it saves the state that it was operating on onto its stack, calls yield. Yield ends up going back to routine A by switching stacks and restores the state that we saved back up here. So yield effectively returns to the code running there. We make some progress, and yield gets called again, etc. And so we're running two routines, never concurrently because we're a unit processor, but it allows us to get to a point in execution and basically say, give someone else a turn for a while. And eventually that function will return after either a scheduler or somebody else yields in a way that allows routine A to continue. Okay, so here's our bit of code again. We're running in a coroutine environment. We've got a function. We assign A, we call some other function, and we've got our usual sort of weird test that assigns to. And the question is, what's the value of A again? Exactly, it depends on whether function 2 calls yield. Okay, so this creates something that ideally in a programming model you don't want to contemplate, i.e. you don't really want to know what happens inside libraries that you call deep in some other environment in code that you didn't actually necessarily write. But with this model, you have to know. Okay, in more shall we say, principled programming languages, you might have whether the function yields on the type. So if you're programming in Haskell or one of the other more modern languages, you can basically annotate the type of the function, whether it yields or not, and then from that, you can have the compiler sanity check assumptions about whether yield was called or not. So for instance, if this function is declared as a non-yielding function, and this guy yields, and as of the type it yields, then the compiler can tell you that, well, hang on, there's a mismatch here. You really know what you're programming. Okay? But in C, you don't. Okay? In C, you basically have to understand okay, I'm calling a function. Does that function yield, or is it, or does it not yield? If it yields, then that changes the way I have to think about the code that I write. So if it's a yielding function, then I have to consider these two parts as basically mutually exclusive, with the potential for things to change completely in the middle here. If it's a non-yielding function, then I can consider this. Okay. So the ability to yield has allowed us to support long-running functions and to wait for things by allowing other activities to occur. But in return, we've got this extra complexity on how to think about what's going on in the system and what may or may not change in code. Okay, so any queries at this point? Nope. Okay. Okay, so this slide kind of, I think, is a summary of the previous slide. So basically, when subroutines and with coroutines, you've got this issue of what actually happens inside the subroutine that you have to consider in determining whether you need to reason about effectively concurrently with other coroutines or not. So the nice thing about this model is that for the majority of time, you don't need to reason about currency because yields are usually not involved, and you've got this nice sort of straight line sequential code that you can program without having to put your mind about concurrency. Okay. However, you need to confirm that there actually is no concurrency via the presence of not yielding. Yep. So the question then becomes, well, can we, again, in return for some more complexity, be a little bit more systematic and make the model slightly more complex and not have to worry about yields? Okay, and the answer is yes. We can to cooperative multithreading. Okay. Cooperative multithreading is sometimes called green threads. I don't remember the history of why they're green. Okay, I'm going to guess there was a Mr. Green or a Miss Green who wrote the thread library, but I don't know, maybe Google and get back to me in the lecture if you figure it out. So what the idea behind this is that we conservatively assume that we've got a multi-threading model, even though it's not preemptive. So that implies that we use synchronization, the locks, to explicitly avoid races. Okay? And this allows us to make no assumptions about the subroutine behavior with respect to yield. Okay? We still have to worry about whether subroutines end up causing deadlocks with ourselves now that we've got synchronization primitives involved. Okay, but I'll talk more about that in other slides. But if we've got locks, then we can then relieve ourselves of the burden of having to worry about whether something yields or not. But if we've got locks, we've now got the burden of actually synchronizing explicitly. So here's our bit of code again. And I'll ask the usual question, what does this function return? 2. There is one assumption here that's pretty implicit, that everyone kind of assumes that it's true, but I'll just make it explicit.
Function 2 doesn't modify A.
Yeah, we're assuming that function 2 either attempts to synchronize, any other activities in the system that attempt to access A also synchronize appropriately. Okay. So given this model, we can now basically not have to worry about, okay? But now we have to worry about locks. So given we've got threads, let's have a look at the implementation using a diagram again, where we've got a CPU running a single thread of control on the yellow stack. And where's my diagram going? Okay, so threads have a little bit more baggage than coroutines. So a thread will basically have state related to program counters, stack pointers, registers, and so forth. But they will also have some baggage associated with the state of the thread itself that the runtime environment provides or keeps track of. Okay, so this runtime might be user level threads, if this is a user level threads pack, or it might be the baggage associated with the threading that exists inside the operating system itself. Okay, so I'm not distinguishing necessarily between the two. So, given that we can synchronize, we may be in a running state or blocked. We may have the idea of thread IDs that we can switch in between and manage. We've got schedulers that may have queues and priority. And so we will have this idea of I remember where my slide goes, a thread control block. Okay, per thread that keeps track of this information relating to the thread. And so a thread can be effectively captured, i.e. we can store the state of where it is at a particular point in time, by having a split between the state that is stored on the stack and the state that may be stored in the thread control block. Okay, the precise blend between the two actually varies between different operating systems. So, for instance, just to use an example, if I'm saving the state of the register set, some operating systems will dump that state into a thread control block, and some operating systems will push it on the stack. Okay, it doesn't really matter which one for this purpose. So if we have a thread B and a thread A, we may have, we will have a separate thread control block and a separate stack per thread. Okay, so just to switch between the two, again, this is very similar in the mechanics, but not necessarily in the semantics, of saving the state of the registers onto the stack, and then stacks, and then restoring the state of the other thread. So basically give, and where's this adding going? Okay. Apologies. So we're currently running the yellow thread on the CPU, and we save the state into the thread control block, this particular animation, and we load up the state of the green thread, and we're now running the thread of the thread B rather than thread A as such. So to implement this, I've borrowed a little bit of OS 161 code again, but I've put the surrounding code that calls the switching assembly to give it a little bit of context. So this is the thread that, this is the code that gets called when we decide we want to switch. So this might be the interrupt handler. Okay, the timer interrupt calls switch, and the switch calls the scheduler to say, okay, who am I going to run next? We save the ID of the current thread. So that actually implies that this model has the idea of the current thread as a global that's always consistent throughout the system. And you saw that with the OS 161 programming last term. It kept track of a current thread pointer that always pointed to the current thread, and whenever it switched, it was kept up to date. So you could rely on the thread to always point to the bookkeeping associated with the current thread. So we save the current thread, we set the current thread to be next, and then we call the magic assembly with the two pointers of the current thread and the next thread. And then we back into this code that looks suspiciously like the coroutine switch code, where we save on the stack, the state of the current thread. So we're basically just pushing all this onto the stack, and then we store in that first argument, i.e. the current thread control block, the stack pointer that we resulted in. So now we've captured the entire state of that thread on the stack and stored the stack pointer that points to where we left off. We load the stack pointer of the next that the scheduler picked. So now we've switched stacks, and we can restore all the registers, i.e. pop off the stack, all the state of the thread that we switched to, and then return to the point in the thread that we switched to of where it left off when it saved its state, and it continues. So now we switch between the two. And it's 55 past, so I might take a break for 10 minutes rather than push through. Yeah. So sorry, it was from Sun, but?
The green team.
The green team. Ah, interesting. So green threads came from the green team. Yeah. Okay, so we're back online. So regarding the labs, I'll encourage you to use the lab demonstrators for mentors as much time as they have, so to speak. What I've done is provided them with some guidance to prioritize milestone marking over mentoring. But once the milestone marking is done, feel free to run designs by them or get them to help out with a bit of guidance as much as you need or like, okay? Given the enrollments are varying, or sort of trending as people decide whether they want to commit to the course or not, it's unclear that we've got the staffing level right, so we will evolve based on need as the semester goes. Okay, so we've taken an initial stab at sort of this hybrid, some in the lab, some online available for the term. We'll see how that goes. In an ideal world, it'd be great if everyone was just back in the lab and the lab demonstrators were just back in the lab, but we do have some part of the cohort, last time I looked, that was still overseas. And so we will be sticking with the hybrid model. But I'd encourage you to be face-to-face because it's just so much more efficient helping somebody through their code when you're in the same room as them rather than online, okay? I'll go back to lecturing, but I'll give you a chance to ask questions about the project and so forth at the end of the lecture, just because I don't want to run out of time if we end up off on a tangent for the next 10 minutes. Let's get back to business, and then I'll talk more at the end, give you the opportunity to ask questions at the end. Okay, so where are we? So we're back into this switching model between threads, or with threads, where effectively a thread is executing and we save the state, switch stacks and restore the other thread, allow it to execute, save state, switch back, restore the state that was stored previously within that thread on its stack in order to allow it to continue. Now, I guess the observation that one should make here that I wasn't explicit with the coroutines as well is from a thread's perspective and a coroutine's perspective, execution is the fact that we've switched to something else and come back is transparent, except for the concurrency issue in the coroutine that wasn't there unless we yielded. Okay? In threads, we basically conservatively assume that we may have switched. So in some sense, we've made that as an unknown and we've conservatively synchronized so that we just assume that we've got sequential execution from start to finish with potential parallel activities. So let's go to the next level and introduce preemptive multithreading. Now, preemptive multithreading is the same as multithreading, except that we no longer explicitly trigger the thread switch. Okay? The thread switch is triggered asynchronously by arranging for a timer interrupt to invoke the scheduler, and the scheduler then triggers the decision as to whether to switch and who to switch to. Okay? So now, if you're looking at the multi-threaded model as we had previously without being preemptive, you kind of might have gone, oh, yeah, I know it's not going to switch there. I can make some assumptions that would actually violate the model of being multi-threaded versus coroutines, because you shouldn't make those assumptions in a multi-threaded environment. Now, if we're preemptive, you can no longer even sort of squint and violate the model but make it work. Now, you have no control over when the switching occurs. And if you play those games, you'll end up introducing race conditions that breaks your code. Okay? So that's multi-threading. So if you look at threads on a simple CPU with no protection, you'd have a model that's something like this, where we've got scheduling and switching introduced, and we have, again, thread control blocks and stacks. And if we have threads on a CPU with protection, then inside the kernel, we've got threads, thread control blocks, and this model here should be relatively familiar from the environment that you had with OS 161. Okay, it had an environment where you had multiple threads of control within the operating system itself, and application code such that for each application running at user level, there was a thread of control within the operating system explicitly associated with that specific application. Okay. So to switch between applications, the application would have done a system call, or a timer interrupt may have occurred, or some other kind of interrupt, resulting in a transition from running the user code into the OS code. The OS code, let's assume it was a timer tick, decided it may want to switch to a different application. Then we'd end up saving the state of the application onto the kernel stack, and then basically changing the idea of the current thread and the current process to a different stack. And then when we return back to the application, we'd end up with this situation where we're no longer running thread A, we're now running thread B. Okay? Because we've changed the view of memory when we did the switch. So that context switching code that we've looked at previously that simply switched the thread, there's obviously a little bit more baggage associated with it now. You've got to actually change the idea of what the application address space looks like to go from the yellow thread A to the green thread B. Okay? So any queries at this point? Okay. So that should be a very familiar model to you based on the practical work that we did last term. So what's this? No. What's the alternative? Yes. So this is user level threads. Okay. So kernel level threads would be an environment like this where we have multiple threads of control, i.e. another stack. Oh, my writing is awful today. Stack. It hasn't got better. Such that we end up with a multiple stacks associated with the green process. Another stack. Yeah. So that would have been kernel level threads where we have a thread of execution within the operating system for each thread at application level. Here we've got user level threads for two reasons. Let's assume, as the slide indicates, that we're running the yellow process. Okay? There's only one yellow process here. Okay? And there's a lot of strange odd colors here representing multiple threads of control within this particular process. And the giveaway is scheduling and switching within the application. Okay? So we've got a scheduler that's choosing between threads of control within the application. And we've got and indirectly, no association between the thread that exists inside the kernel and the threads that exist inside the application. Okay. So that's basically this model that we saw last term. Okay, where we've got multiple threads of control that are cheap to synchronize, create, etc., but have the usual problem of if they call into the operating system and block, one thread blocked within the OS for process A effectively prevents any progress for any of the other threads that exist inside process A because the operating system has no knowledge of them. Okay? Same thing with page faults. Okay? If I take a page fault with one of these threads into the OS, and we block waiting on feeding some data in from disk, then all the other threads within that process can't make progress. Okay? So I didn't talk about this in the base course, but if you're attempting to be clever, and one can, and use asynchronous system calls into the OS to avoid blocking inside the OS in order to maximize the amount of computation between each of these threads by issuing asynchronous demands onto the operating system so that the operating system effectively signals when things are available so we don't block within the OS. Page faults still bite you. Okay? You might be able to avoid blocking system calls, but page faults are something that the applications don't control because it's transparent. Okay? So I think, and the other one is there's no thread level parallelism on a multiprocessor with user level threads. Okay, because there's nothing that the OS can pick up and schedule on a separate CPU. Kernel level threads that we all know as well, just to recap, are more expensive to manage and synchronize because we've got to cross this user kernel boundary to block and unblock because the OS does that work. The OS does the creation of the threads because it needs to keep track of bookkeeping and stacks on the kernel side for each of the threads of control on the user side. But the win here is we can do blocking system calls and the OS can pick some other level of parallel runnable thread within the same process to keep the machine busy. Page faults also result in potentially switching to a different thread that's runnable within the same process. So we could keep a multiprocessor machine busy with a single application running on it. Whereas with the user level threads, if we only have one application and we've got 10 CPUs, we're going to have 9 idle CPUs, okay, if we're only running one application. So I think I've just mentioned that. Yep. So let's look at continuations. Okay. So what is a continuation? This is one of those things that can be difficult to grasp, especially I'm going to use some functional programming examples as well, just to keep you on your toes. So a continuation you can think of as a representation of the state of the system at a point in time, and also the state where you would like the code to continue from. Okay? So one thing you might call it is like I want to snapshot this point here in order to be able to transition to that point after I've done something. Okay? I'd like to continue from a particular point. So let's use Python before we get into the functional programming, just to give you a bit of intuition as to what I mean by a continuation. Okay? So here's a traditional function that takes an argument and returns 1 plus the argument. Okay? That's obvious. Okay? We're all familiar with calling a function and the function returning a value. Now, implicit in this is the idea that a function returns back to where it was called from. Okay? Continuations don't assume that. Okay? The idea behind a continuation is that you specify what happens after whatever it is done and where to continue from. Okay? So here we have a continuation-like struct where we pass in the argument and we pass in the continuation of where we would like this function to go to when it's done. Okay? And in this example in Python, it's a function. In an example, in a language with first-class continuations, it would be a continuation type. Okay, and we'll see that in a moment. And so instead of returning to where we called from, after we add 1 to the first argument, we then call where we have to go to. Okay, we don't return. Now, depending on what that continuation contains, calling it may actually take us back to where we go. Okay? Or calling it may take us to somewhere where we need to go. So let's use another example while you're all looking confused to see whether it makes it a little clearer. So there is something called continuation passing style, which if you've done compilers or sort of low-level programming language fundamentals course, you may have seen before. Okay. So what we've got here is a function that takes 2 arguments and multiply the first one by 2 and add the second one. Okay. And then return the result. That's the traditional view. Okay. Now, if we rearrange this into continuation passing style, rather than simply relying on returning the way the function's called, then we can break this down into each of the fundamental bits of computation and explicitly tell the programming language where we want to go to next for each of these little fundamentals. So here's a function that multiplies A and B together and then goes to whatever the continuation happens to be. Here's a function that adds A and B together and then goes to whatever the continuation happens to be. And here's our original function in continuation passing style. Okay. So hands up who's unfamiliar with lambda functions. Okay, lots of people. Okay, a lambda function is basically an anonymous function definition on the fly. Okay. That's probably not enough to have you completely grasp it. So you can think of this lambda function here as being a function that takes 3 arguments. So let's call it, see if I can write clearly, anon, v, y, and the continuation. And what this function does is it calls add for v, y, and the continuation. Okay, so imagine we've got this function defined. Let's make it a bit more Python-like. Oops. Imagine that we've managed to insert that function here on the fly. Okay, that's what a lambda function is. It's basically a quick and easy anonymous function definition supported by the language. If you do any functional programming, you'll do the functional programming course, you will see lambda functions pretty regularly. It's just a way of coming up with just a local function definition on the fly without having to create it with visible anywhere else other than just where you put it in the code. And that's not the best definition I've ever gave, but anyway. So walking through this in continuation parsing style, if we have an x and a y, and where we would like to go to after this whole thing is completed, what we end up doing here is we call multiply with the 2 and x, passing in this function of where to go to next. Okay. So if we go to multiply, we'll end up with a 2 here and an x, and the lambda function, which I'll represent as an L. So what we end up doing is multiplying the 2 and the x together, which is, okay, that's good. We seem to be performing what we'd like to perform. And then we go to whatever the continuation happens to be, which is the lambda function. Okay? So we call the lambda function with the result of a times b. So the lambda function takes the a times b, and we've got y and the original continuation, and it calls add on effectively 2 times x, b, which happens to be y, and the original continuation that was passed into the function. Okay, so that will add 2x and y, and then we'll call whatever the continuation happened to be there originally. So you can see what we've done now is we've basically broken this up into a 2x, a call to a plus y, and a call to wherever we want it to finish up. Okay, so we basically broken it up into different continuations, and the continuation is where we'd like to go to when we're done. So you can imagine you could build a computation model using these basic building blocks where, in addition to passing in the arguments for whatever it is you want to compute, you pass in where you want it to go to after it's done. Okay? And this can be really generic. You can, shall I talk about? No, I'll talk about it a little bit more later. Okay? So that's the intuition that I wanted to introduce before I bombard you with a little bit of functional programming syntax. Okay? So one of the original implementations of first-class support in a language for continuations was in Scheme. Okay? Scheme is a Lisp-like language, so for the Emacs users around here, you'll be going, okay, this all looks completely familiar, but given Emacs is not so popular anymore, I suspect I'm working with a clean slate. So call CC is call with current continuation. And this function takes a function as an argument. Don't worry, the example's coming. Takes a function as an argument and calls that function and passes as its first argument to the function that it's called a continuation that represents this particular point. Okay? And later, when that continuation is called, we will return back to where call with current continuation was called originally. Now, this is not the kind of a concept that is really amenable to hand waving. So obviously here comes a slide. So we've got some Lisp-like code, i.e. scheme code, and we're executing along. And we have a function defined as f, and we call with current continuation f. Okay? So call with current continuation creates a continuation that represents this point here, where we would return back to, and wraps that up into a function that can be called. Okay? So let's basically call that C, because I'm not very original. And what call with current continuation does is it calls the function f that we passed in with C as the argument to f. So the continuation, C, that represents that point in time here is passed in the argument to f. So inside f we can do whatever. And at the point here, we invoke the continuation with some arguments. What happens at that point is that the code goes to the continuation where we should continue from, which happens to be here, so basically warps to that point there, and returns whatever the arguments happen to be to the continuation. So effectively, this call with current continuation will return with remaining arg, and what we've effectively implemented using this call with current continuation is a return operator that allows us to warp back to the point where the function was originally called without actually having return in the language. So I think I've got actually that, no I haven't, another slide coming. So for C programmers trying to wrap their brain around this, you can think of call with current continuation effectively saving the point at the stack and the program counter such that we can then go back to that point on the stack and program counter at some point in the future. Now, there are lots of different implementation strategies, and there's whole papers on most efficient or least efficient way of implementing call with continuation or continuation-like operators within languages. I'm not going to delve into that. What I'm trying to do is just get you a feeling for the insight that the continuation sort of represents the state and the location of where you would like to continue from in the future, so that we can then use that concept to figure out, well, I'm in an operating system, and at some point in the future, I'd like to go back to doing what I was doing. Can I use this concept of continuations to structure my OS so that I can return to things in the future? Okay? But that's coming. So here's a implementation of a return operator, and we've got a Lambda function, so I am so glad that I've already introduced that and everybody's complete expert with Lambda functions. So what we've got here is a function in scheme syntax called f that takes one argument. And that first argument must be a function, because what we do is we apply the argument to the number 2, and then we return 3, because it's the end of the function. Okay? So let's play a few mind games here. So if I call display on f, and the function that I pass it is effectively an identity function created on the fly using a Lambda function. So it just basically takes the argument 2 and produces 2. And I display the result of this. What happens is the Lambda function gets passed in here. We run the Lambda function on 2 and it produces 2. So somewhere in this representation there's a 2. But then we get to the next part of the function, and we end up returning 3. So display f of lambda identity ends up displaying 3. That's kind of what you would expect. Now let's play the same game with call with current continuation. So if we display call with current continuation f, remember call with current continuation basically creates a function that represents returning from call with current continuation to this point here. And it then calls the function f and passes as an argument the function that allows us to warp back to this point. So the continuation gets passed in as the argument to f. So this line of code here now is invoke the continuation function, passing it the argument 2. So that means we end up warping back to this point here, returning 2, and we never execute the 3 because we just go back to where we continue from. Yep?
Yeah, so is this basically a way of like converting, so to speak, from continuation passing style back to like normal functions, so to speak?
That's not a point I'm trying to make, but indirectly, yes. So one of the example here is that you can implement a return function in your language using continuations as the basic foundation within the language. You could layer a return operator on top, which is kind of what I've done here. Where continuations also pop in, if we're going to have a slight divergence in the discussion, is imagine exceptions in the programming language, where you basically have catch and throw. Catch is effectively saving a continuation of a point in your code, and throw is effectively invoke the continuation and walk back to that point. So the structure in the language, you could imagine implementing catch and throw using a continuation operator on top of a language that actually didn't have exceptions like that in order to provide them, rather than having to have those language operators basically hard-coded into the compiler. You can also have things like, well, my standard mode of operating with a function definition might be must pass a continuation if I succeed and must pass a continuation of where to go if I fail. And so usually if you succeed, you'll simply return. And if you fail, you would probably return back to wherever the catch happened to be. Okay, so for those of you who are familiar with catch and throw as exceptions, can kind of see how this could be laid on top of a continuation-like operator within the language. So yeah, indirectly, good question.
So in terms of jumping around logically, it's kind of like a go-to that you save the state.
Yeah, I've got another sort of mind bender coming up, and ask your question after this one. So, in Scheme, functions are first class, so you can just assign them to a variable. So what we've declared here is a variable that's a function type, and bear with me, I'm not a Scheme programmer, so I may be sort of abusing the description of the syntax somewhat, but I'm here to make a point, not teach you Scheme. So we declare a variable called the continuation that we're going to use to store the continuation in. Okay? So thus far, you've seen that it's basically being passed as an argument. You can also take that argument and store it somewhere and invoke the continuation as many times as you like. So we've got a function called test. Test has a local variable called I, and we set that variable to 0. So we initialize I as 0. And then we call with continuation, which sets this point here as the continuation, and our lambda function, which effectively is going to receive the continuation as an argument, saves the continuation into the continuation variable. So what we've got at this point in test is we've snaffled away a continuation representing the execution at this particular point in time in a variable. Okay? Then we increment I, and we return I. Okay? So that, I think, is relatively straightforward. We've saved the continuation that represents this particular point here, and we've incremented I and returned it. Okay, so now let's play the mind games. So we call test. Test saves the continuation. Initialized I to 0, returns I after it increments it, and we get 1. Now we've got a continuation lying around, so let's call it. And so it warps back into that same function with its current state, which happens to be 1, and increments it. Okay, so now we've got 2. Without calling test. We've just basically continued from within the function. Let's do it again. And now we get 3, because we've warped back into the middle of the function with its current state. Now, let's make a copy of the continuation, because this is a functional programming language with garbage collection, and it can do all this kind of stuff, copying all the machinery and stacks and managing allocation and freeing and so forth in the background. So let's just make a copy of that continuation. And let's call test again. Recall test basically sets the continuation, the variable, to, or sets I to 0 and stores a new continuation in the continuation. So now, after test returns 1, we can call the continuation for that instance, and we get 2, because basically it's just incrementing. But we've also got this old copy of the continuation lying around with the old state, that if we call that, we'll get 4. So now we've got 2 continuations to the same function that have independent state of each other, and we can use them to invoke that particular point in time independently of the other. Okay? So you could imagine in the background, a lot of people think in terms of implementation, yeah, what we're doing is we've got independent stacks, and copying a continuation to another continuation ends up making a new stack that has the old state, and all this stuff is basically moved around in the background. Okay?
So if you call the continuation afterwards, it'll return 3.
Yes, it'll keep plugging through. So now we can play some pretty good mind games. Let's implement fork. Okay, so our aim in life here is that we want to fork off a new thread of control that runs process. Okay, process is the name of the function that's going to start running in the new thread of control. Okay. So what we're going to do is we're going to call current continuation, because that's going to save the point that we're at in the current execution. Okay, so that's effectively saving our state. And then we're going to use a lambda function again, where k is effectively that continuation of where we currently are. We're going to enqueue that into a list. So we've stuck where we are, or where we were at that point of that call to current continuation, and we've put that into a list. So we can get back to it in the future if we ever pull it out of the list. And then we simply call the process. Okay, proc, which is a function. So we've got it stored where we were, and we're now running something different, but we could always go back to where we were. And so here's an example of an implementation of yield. So yield calls with current continuation to save where we are when we call yield. And the lambda function, k again, will be the continuation that we just saved of where we were. We enqueue that onto the list, and then we just dequeue whatever was in the list before, which effectively evokes the continuation which warps to whatever we were in the past. So now we've implemented effectively coroutines within a language that doesn't have them, using call with current continuation to save state. So it's a really sort of powerful idea of recording where you would like to go back to in the future. So the emphasis that I'm trying to make here is not so much on continuation passing style, which really makes people's heads hurt in terms of both reading code if someone writes code in that style. It's more about thinking about saving what you need in order to restart something in the future. Okay, and that will pop up in terms of the assignment when I talk about that a little more later. So, continuations you may have seen in your C programming careers. The definition of a continuation varies. There's actually a nice paper out there that sort of talks about 6 or 7 different people who independently invented something that looked like a continuation that didn't really call it a continuation in the history of computer science. I should have actually put the reference up here. And so continuations are kind of at a high level is just really what I've described. It's the idea of representing where to continue from in the future. More specific things like closures in programming languages end up just making the continuation somewhat more precise in detail, like it defines the scope of what data is visible when you arrive in the future and what the representation is of the computation and so forth. Continuations to me is the sort of the more general thing. And so one manifestation of a continuation happens to be set jump, long jump in C, which is what tends to be called a one-shot continuation because it only works once. Because there's no sort of magic in the background copying stacks around that allows you to make copies of the continuation and invoke it multiple times. And so set jump, long jump, which records where you are in C and where you are on the stack and allows you to jump back to it, only works once. Okay? And it's what tends to be used in a high-level language as implemented on C to implement that idea of catch and throw, okay, by the compiler. So what should a kernel's execution model be? Okay. The aim here is to not point out a right and a wrong. The aim here is to give you enough background for you to make a judgment call for yourself because there are trade-offs, and naturally in some situations one trade-off might be more appropriate than another. So at a high level, if we're going to divide this in two, is that you can build an operating system with a single kernel stack, or you can build an operating system with multiple kernel stacks. And that largely will pigeonhole you into events versus threads. Okay. So how are we doing time-wise? Yeah, I think I've got time to start this. Yeah, we'll see. Okay, so with the per thread kernel stack model, okay, that's also sometimes called the process model. It's the model that you're familiar with OS 161, where the thread state is implicitly encoded on the kernel's stack, and there's one stack for each activity within the operating system. Okay, so just to contrast it with continuations, now that we've seen continuations, each function, basically local variables, as we basically nest functions as we call through them. The compiler is basically generating code that's implicitly reserving space for local variables and storing them on the stack. And if we want to switch to a different activity, we basically switch to a different stack, as opposed to something like continuations, where we would explicitly manage where local state might be or not be, and switch to a different continuation in order to resume a different activity that was somehow recorded in the past, etc. So the programming model that we can use with thread-based is actually, what I'll point out here, is really simple. Okay, so what I've got here is a bit of code. It's unfortunate I'm introducing it right at the end, but hey, I'll pick it up again next week, where the example takes 2 arguments. We call P1, which does whatever with those two arguments. And for reasons that will become apparent later on, we can test to see if we need to block. Okay? If we need to block, we call thread block. Thread block eventually returns. And then we invoke P2 on the second argument. If we didn't need to block, we just call P3 with no arguments, and then we just return. Now, the point I'm trying to make here is that if you're looking at this code and trying to understand what's going on, it's simple in the sense that you're not concerned about what's happening inside thread block, because this is a thread-based model, okay, running on your own private stack. And what happened inside thread block is transparent to you. So logically, you can read this code and reason about it in your heads just by going from start to finish. Okay? You're not having to worry about, did the thread block throw away everything that I was working on such that I somehow have to get it all back after I return from thread block? No. Okay? This is just would be straightforward sequential thread-based programming that you've seen in the past. And also, if we have preemptive multithreading, yeah, sure, there's concurrency issues here that you might have to deal with, but it doesn't change the fact that you look at this code and you read it from top to bottom. Okay? And you can follow it through the different paths that may or may not occur. And you can do that independently of whatever else happens to be potentially running in the system. So let's have a look at the single kernel stack model, which is the event-based model as I've called it, but sometimes this is called the interrupt model, okay? Where, because largely they've called things that trigger the need to react to something for the operating system an interrupt, okay? You could call it an exception-based model as well, but let's call it an event-based model just to be consistent. So, how does a single kernel stack support many threads? And the fundamental issue here that ends up becoming tricky is, how do we support system calls that block if we've only got a single stack? Because we saw in the previous model, we just called thread block, and if it really blocked, my state would have got saved on my stack. Someone else's stack would have got used for other execution, and then I would have been resumed on my stack. Thread block would return to me, and I didn't really need to do anything about it. How do we deal with the requirement where I've got to the point in my code where I can see I can't progress, but I can't block because there's only one stack, and I can't tie up that stack until whatever it is that I'm waiting for occurs? Okay. So there's basically a couple of options here. One is continuations. If you want to read about the application of continuations to an operating system, there's a classic paper where they applied continuations to Mark, which is the, is Gernot talked about microkernels and Mark yet? Yes. Okay, so basis of the Mac. In using continuations inside Mark back in '91. They're not there now. Or you have what's called a stateless kernel, where the interface, all the system calls are effectively atomic and they can't block, and that implies there's that the restrictions on the kinds of system calls that your operating system can provide. Okay, and the classic paper for that one is the Fluke paper back in '99, where they built a microkernel that could be switched between both the process model, i.e. the threads inside the operating system multi-stack model, and the single stack model, and they did some performance analysis and benchmarks and so forth between the two variants of notionally the same operating system running in the two different variants. SEL4 is also a mostly event-based model of a operating system. And we're doing time-wise. Let's call it quits there because, yeah, I don't want it to be cut off in the recording, in echo, and I don't want to rush this because this is kind of the crux of why I introduce continuations. So I will see you tomorrow afternoon, I guess. Okay.